So today we are measuring the performance of a hot dog as an infinite fin. So you can see we have 3 hot dogs on this structure here, suspended over boiling water. And above that water we have some aluminum foil to insulate that water, and also to keep as much steam away from the surfaces of the dogs as possible. So on the individual hot dogs, you can see we have marks. These are 6 centimeters away from the foil. And since there's a lot of steam under that foil, that should be our surface, all at 100 degrees Celsius. And so periodically I'll be measuring with this little thermometer right here, measuring the temperature of the hot dog. And once it steadies out, then we can make our measurements at our X value of 6 centimeters. Okay, so we had some steam issues. So I have this hair dryer on low, blowing away the steam. This is in Fahrenheit, so I'll convert it later. But I'm sticking the probe straight into the mark that I made at 6 centimeters. 75.5 is close to 25-ish degrees Celsius, maybe a little lower. So it's about 4 degrees above ambient temperature. And just one thing to mention, when I stick the thermometer in the top of the hot dog, it does come out to right about ambient. So that says that we are having the infinite fin condition. T surface does equal T infinity. And so we are using the correct model in the next step, which is nice. It makes life a lot easier. So this is our model. From the experiment, we found our temperature 6 centimeters up the hot dog to be 25.8 degrees Celsius. This was the temperature in 2 of the hot dogs. The third, I noticed in the video, was a bit higher up than the other 2, so I decided to just throw out that data, but the other 2 had the exact same temperature. So here are constants. The first is our K value, and this was found in an academic paper published by 2 Georgia Tech scientists in 1984. They boiled hot dogs and they found the K value. And then all the other ones are measured values, so our cross-sectional area, the length of the hot dog, the point at which we measure temperature, the diameter of our hot dog, our p-value, our ambient air temperature, and the temperature at the base of the hot dog. So we also have our assumptions. The first is steady state, which we did verify. The hot dogs were boiling for about an hour, and about 45 minutes into that hour, they had reached a constant temperature. So after 15 minutes at constant temperature, I decided we were at steady state, and that's when I measured our Tx value. And so the next one is constant K and H values, negligible radiation, one-dimensional conduction along the hot dog, and then infinitely long dog. There's a equation in the textbook. It says that if the length is 2.65 times the m value, the little m value of the hot dog, then you can say that's infinite. And it turns out that this hot dog fit that consideration, so we could call it an infinitely long dog. So moving on to the math, the first thing we had to do was solve for h, since that is our one unknown. So using the infinitely long equation for theta over theta b, we solved for h and then found that it was 7.395 watts per meter squared of Kelvin. And this is this falls within the range of acceptable values for air. It is a bit lower than I expected since I was constantly blowing it with a hairdryer, but since both of the hot dogs gave the same temperature, I'm taking this to be true. And then next is our fin performance, and this is another equation from the textbook. And so what it says is that if the performance is greater than or equal to 2, the use of that fin is justifiable. So our value was 3.144, which means that the hot dog is in fact a justifiable fin. So if you want to cool something down, theoretically, according to these results, you can just slap a bunch of hot dogs on it and it should cool it down.